So this is your Lab 14. This is just understanding basic Ohm's law and meter usage is the whole intent behind this lab. The first exercise that we're going to start with is just ohming a harness. This is not unlike what you would do in the industry where the big difference is this harness is super short, but I've got the wires all shorted inside, and I have some with diodes in them and things like that are intended to help you practice it with your own meter. This is a similar exercise that we would do in real life on a vehicle where I may have a harness like this that's up at the front of the vehicle, and it may go to a computer or a PCM like this that it would plug into that connector, and then it may run 10 feet towards the back of the vehicle to some other components. And sometimes you'll have wires that will short together either because somebody left them on the exhaust manifold and they melted the insulation, or maybe they pinched them in a bracket and then wore through, or sometimes the insulation just deteriorates with age. You get oil on the wire, sometimes it'll break down the insulation, or maybe like we talked about before, that somebody put too big a fuse in, that they were blowing fuses and they put a bigger and bigger one, and then they lit the wire on fire and it melted them all together. And so there can be a variety of reasons why a wiring harness will get shorted together, but they can short together. So we're going to go ahead and go through the exercise of ohming this harness. Now, these are the little benchtop trainers that I have that I just made up to have people exercise and practice with Ohm's law and practice with their meters. But what we have is just a regular automotive battery. It's got a little switch and it's got a fuse in place. And then we've got a couple leads from either end of this battery. And then there's a metal bracket over here which is intended to kind of represent the ground that you would have on cars, or a chassis ground, that everything metal on the car is the ground path. And so if we're going to ohm this harness, what we're going to do and what's in the lab book is we've got all these different color wires that we would have for the harness like this, all our variety of different color wires. And there's a little diagram that's in the lab book that looks like this, that we're going to ohm red to red and see what the resistance is on that wire, and then make sure it's not shorted to any other wires, and then that it doesn't have a diode in it. And so we're going to go ahead and go through that exercise. Like I mentioned, when you turn your meter over to ohms, then once you have it on ohms, then you want to touch your leads together and make sure that your leads are good. We're also going to want to be careful that we don't touch both leads at the same time. So on here, the first thing we'll do is we'll pick our red wire and we'll clip in on our red wire there, and then our red wire here. So then our resistance value right now is 100.6 ohms. So I do have red connected to red, so we'll draw it through there, and we have 100.6 ohms. So I want to make sure I don't have the kilo symbol up there, so there's no prefix there in the upper corner. So this is just a straight 100 ohms. Now I want to make sure that it doesn't have a diode in it. So I'll take the polarity of my leads and I'll switch it. So I'll put my red one over here now and my black lead over here. So it's still the same 100.6 ohms, so there's no diode in it. If it did have a diode, then it would block and it would read open circuit in this direction. So now I'll just make sure that I don't have any wires shorted together. This is an auto ranging meter, which I recommend that you do get. We don't want to have to, some of them are manually ranging where you'd say, it'll read from 0 to 1,000 ohms, and then 1,000 to 100,000, and then 100,000 to 500,000, and 500,000 to 1,000,000, and then to 10 million ohms. You don't want one that has a variety of different scales. You want one that'll auto range like this, because that enables you to go and just touch these wires quickly. If the meter stays at open circuit the whole time as I touch each one of these wires, which it has so far, so then I know that none of them are shorted together. So then I'll check the other side of the harness real quick. And if this was a harness on a car, then we would also touch ground and make sure that it's not that wire's not shorted to ground. So this one is open to all the other wires, so we just draw red across to red. It's not shorted to any other wires. So now we'll move to our blue. So if I go to my blue wire, blue to blue. So blue to blue is 0.2 of an ohm. So that's good. Now if I check my polarity and switch my red lead to the other side, still 0.2 of an ohm. So blue is connected to blue. 0.2 of an ohm. And then now we'll see if it's shorted to any other wires. So there's blue. I'll just check these guys real quick and make sure it's not shorted to any of these. There's to brown. There's yellow. So blue is shorted to yellow. I have 0.2 of an ohm to yellow. Nothing to orange, nothing to red. I'll check here on the other side just real quick. Nothing to brown. Shorted to yellow. All right. So then we'll just draw a line over to yellow. So blue and yellow are also connected. So then now we'll check the next one, which is our black wire. Go black to black. OL. So black right now is showing an open circuit. So now I'll check and see my polarity here and switch my polarity and see if there's maybe a diode in it. Nope. So open circuit on black. So now we'll just check and see if black is connected to any other wires. Nope. All right. So black is an open circuit, so we would just draw a space in this to black. And so another little thing that I would want to share with you is that if I just have wires that cross, they can cross like this. If they're connected in a diagram, then they'll be dotted together, typically like that. So if I, like how this crosses over that one, unless there's a dot in that, then that would represent an electrical symbols that they cross each other, but they're not connected. So now we'll do our brown wire. So first off, we'll go brown to brown. So brown to brown right now is open. Now if I switch the polarity, so I've got an open right now on brown to brown. So then I'll just check and make sure that brown's not shorted to any others. All right, so open circuit on brown. Open circuit, or we could say OL. So open circuit or OL for out of limits. So then check and make sure it's not shorted to any others. I don't remember if I did that, but it's quick enough to do. So then now we'll move to our orange wire. So ohms wire, orange wire is showing OL. Now if I switch my polarity on my orange, then I get 301.8 K ohms. So on orange, I got 301.8 K ohms. So this one has a diode in it. So the way that we draw our diode, little triangle like that with an arrow. So this one's got a diode, 301.8 K ohms. Now we'll make sure that orange isn't shorted to anybody else. Just touch each one of these wires off. Make sure it's not shorted to any others. All right. So then our last one is our yellow wire. which if you can see real well in this camera, then that's actually a green wire with a yellow connector on it. So I didn't have a yellow wire. We got yellow to yellow. It's 0.2 of an ohm. If I switch my polarity, yellow to yellow, same thing. Now I'll just check and make sure it's not shorted. I already know it's shorted to blue. Yep. And so check our other wires. All right. So yellow to yellow is good. It's connected, but I have 0.2 of an ohm. And then I already have it present that it's shorted to blue. All right. So that's it for ohming your harness. That would be the exercise on that. Then the next thing in the lab is to check your open circuit voltage. So if I switch my meter over to DC volts, then all that I'll do is just come over that since this is an open circuit, these are not connected, then this would be my voltage reading for my open circuit. So my open circuit voltage is 12.62. So 12.62 volts is my open circuit voltage. I'm going to erase this so that we can make a quick point about this. So I've got 12.62 volts. All right. Now it has me check working voltage. So working voltage is just now that I'm going to make this battery do some work. So now I'm making it do some work to light that bulb. And if I come back and check my system voltage again, I had 12.62 before, and now I have 12.60. So this is a simple point that this battery is having to push some amperage out into the circuit now to light this bulb. And so what that does is that pulls the voltage down. Our working voltage will be lower than our open circuit voltage. And so if we watch it live even, and I go and I measure it at my battery over here, then instantaneously you're going to see the voltage float back up. We'll see what we have right here. So now I have 12.57. If I open this circuit, then you're going to see this voltage come back to what it was before little by little. Now I'm at 12.58. If it sits here a little longer, it's going to float back up. And so the thing of it is, working voltage, when we make that battery do some work to push some amperage out in the circuit, it's going to draw the voltage down. The largest electrical load that we have on the car is a starter. And so this is a very marginal amount of drop, but it does drop. But when you operate a starter, we may start out at 12.62, and then when you crank the motor, it may draw down to 12 volts during cranking and drop 600 millivolts, right? Or even more in some cases. That the more amperage this battery has to push out into the circuit, the more it's going to pull its voltage down as it does that. So that's a normal thing to happen in a circuit. And so now the instructions on this lab sheet are to get our open circuit voltage, then our working voltage. Now we're going to connect a 2-bulb series circuit. So we got one bulb hooked up. So now we'll grab ourselves a second bulb. We've got our 2-bulb series circuit. So, with our 2-bulb series circuit, we'll connect our circuit there, got both bulbs lit. So now we're going to measure our voltage drop between these two. So, a voltage drop is just the difference in electrical pressure between 2 points. It also represents how many volts of the available voltage that this bulb is using and that this bulb is using. And so, I'll get my alligator clips matching my colors. So if I measure the difference in electrical pressure between here and here for this bulb, this first one. So voltmeters we always hook up in parallel, right? So if I hook my meter up in parallel there, then I'm measuring the difference in electrical pressure between there and there. And for this one, I have 5.058. All right. So this bulb is using 5 of the available 12.6. So now if I check my difference in electrical pressure between here and here, I bet I have 7 something. So I have 7.21. So 7.21 plus 5 point whatever adds back up to our voltage roughly. So that basically divides between these two bulbs there. If I add a third bulb to it and then go and remeasure our voltage drops, that's what we're going to do next. So we'll add ourselves another bulb in series. So now the bulbs get even a little dimmer than what they were before. And now I can come and remeasure my voltage drops. So difference in electrical pressure between there and here. And now this bulb is using 4.708. Now my difference in electrical pressure between here and here. And this bulb is now using 3.2. And then my difference in electrical pressure between here and here. That will capture both sides of that bulb. And this one is now 4.5. So it breaks up now according to the resistance. So I had 3 bulbs, one with 4.5 roughly. This one, bulb 2, the one in the middle, has 3.18. And then this one, my first bulb over here in my series circuit, is using 4.738. So there's bulb 1, bulb 2, and bulb 3. There's my 3 bulbs. So one with 4.7, one with 3.1, and one with 4.5. So which one of these, bulb 1, bulb 2, or bulb 3, has the highest resistance? So hopefully you pick up on the reality that the one with the highest voltage drop has the highest resistance. So this one, my first bulb, has 4.7. It has the highest resistance. This one has the next highest. And then this one has the lowest. And if I add these all up, then that's going to go back and total my source voltage. So in a series circuit, the sum of all the voltage drops equal the source voltage. So the voltage drop of this bulb plus this bulb plus this bulb will equal my source voltage. That couple of things that hopefully you notice is that the intensity of these bulbs gets less and less. When we're doing our voltage drop testing, we're hooking our meter up in parallel each time. So you can see that the intensity of these bulbs, these ones are now brighter than when I go to 3 bulbs. And if I go down to 1 bulb, that one's bright. Gets a little dimmer for 2 bulbs, even dimmer for 3 bulbs. So now we're going to do a parallel circuit. So for my parallel circuit, if I start again with my simple circuit, there. Now I hook a 2 bulb parallel circuit. So for a parallel circuit, everybody gets their own power and ground. So you can see on a parallel circuit, the intensity for each bulb is identical because everybody gets their own power and ground. If I wanted to voltage drop this one, difference in electrical pressure between here and here, then that one is 12.27. Then my difference in electrical pressure between a place to grab on this guy, here and here, 12.31. All right. So everybody though has the exact same available voltage. If I go straight to ground over here, everybody has available to them 12.31-ish, right? If I get a little bit of a bad connection or things like that, then it may be a little bit different. But in a parallel circuit, this guy drops 12 volts and uses 12 volts, and that one uses 12 volts. All right. So the next part of this is we have our Ohm's law formula that we know that with Ohm's law we have victory over automotive repair. And from that, we have three formulas. We say voltage equals, if I didn't know voltage, then voltage equals amperage times resistance. If I didn't know resistance, then resistance equals voltage divided by amperage. And if I didn't know amperage, then amperage equals voltage divided by resistance. All right? So we're, in this one, going to do a calculation, and we're going to calculate the resistance of a bulb. Or we're going to calculate amperage. So to do that, we need to know the voltage, and we need to know the resistance of a bulb. So if I come over and I measure my available voltage, so I have 12.52 volts available. So now we'll measure the resistance of one of our bulbs. So if I snag one of these guys and just clip in as a bench test, right? And we measure the resistance of this bulb, I'll turn it over to ohms. We get 7.1 ohms, all right? So 7.1 ohms. So if we're using this formula, then 12.52 volts divided by 7.1 ohms. All right. So if I grab my little calculator here, and I say 12.52 divided by 7.1. That gives me a calculated amperage of 1.76 amps. All right? So that's what I expect from this bulb, is 1.76 amps. So now we're going to actually measure. So when I hook up to this circuit, it would normally be like this, right? And so now I'm going to hook my amp meter in series. So if I hook my meter up here, and I move my cavity over to amps, and my meter over to amps, I've got it hooked up there. So this meter defaults to AC amps, so we have to push our little yellow button to get it to DC amps. So now what I actually got, my calculated amperage, .76. My actual is 0.2 what? 49 amps. So obviously they don't match. So is Ohm's law a bunch of crap? Or is there an explanation for why they don't match? I'm here to tell you Ohm's law is not a bunch of crap. There is a perfectly logical explanation for why they don't match. If you were here, then this is the way that I always do it. I always go like this. Say, what's the difference between those two bulbs? You know, like, well, one's off and the other one's on. Like, yes. All right. Like, we'll feel them, right? You're like, oh, that one's hot, right? Oof. I always tell my students this. I'm like, did we not talk about that in class? I gave you the rule. Heat causes resistance, and resistance causes heat. When this bulb is off, it's cold compared to when it's on. It gets hotter and hotter to where these will get to the point where they're hot, you can't even touch them. I always tell my students, look, the heat, the moment this bulb turns on, it gets hot. And when it gets hot, its resistance increases. And when its resistance increases, the amperage decreases. I tell them heat causes resistance and resistance causes heat. And if you forget that, and I have to tell you the answer to this by the time you do the lab yourself, then I'm going to stick this bulb to your neck. And it's going to make a little red spot right here, and it's going to kind of look like a hickey. And then you're going to go home to your wife or your girlfriend or your boyfriend or your husband and say, what the heck happened to your neck? And they're going to go, well, oh, Mr. Flint did it. And it's going to get real weird, right? So, I will stick this bulb to your neck, all right? If you forget this and you get it, there's another class you're going to have with me. And if you freaking forget this, I'm going to stick this bulb to your neck. And it's going to burn you, and then you're not going to forget it, all right? And so I'm like the mean dad that you never had, or some of you did have a mean dad. So if you didn't have a mean dad, I'll be your mean dad, all right? If you did have a mean dad, then it's not going to faze you. So, all right. So heat causes resistance, and resistance causes heat. So our actual was about 1/4 of an amp. So the moment that bulb turned on, its resistance went up, so then its amperage went down. Had the resistance stayed 7.1 ohms like when we measured it, then that's the amperage we would have got, all right? But because it got hot the moment we turned it on, the amperage decreased basically instantly, all right? To where if we reverse engineer this and we calculate this, and we say, okay, well, I have 12.52 divided by 0.249. This will give us the actual resistance of this bulb while it's on, which is about 50 ohms. So when the bulb's on, its resistance increased from 7.1 ohms to about 50 ohms, all right? And so then it went through the roof, so then its amperage, decreased. So now the next thing we're going to do is we're going to measure amperage for our 2-bulb series circuit, and then our 3-bulb series circuit, and then our parallel. So we can leave our amp meter hooked up like that, and now we're going to add a bulb. So before I add it, hopefully electricity's become predictable to you by this point, that as I add this bulb, this has resistance, so we were at 1/4 of an amp before. The amperage is going to go down because resistance is going up. So now with our 2-bulb, we have 1.66. So with 2 bulbs, 0.166. So 0.166 amps, all right? 2 bulb. If I go to 3 bulb, then we expect that it's going to what? Go down again. So if I grab another bulb out, and we hook up a 3rd bulb, then our amperage will decrease again. So there's 3 bulbs, and also the intensity of the bulb gets dimmer and dimmer. So here's 3 bulbs. We know, I haven't even looked at it, but we know that it's going to be less than 0.166. So we're at 0.131 of an amp. All right? So now we're going to do our parallel circuit. So if we go back to our simple circuit here, then we've got our same 1/4 of an amp, 250 milliamps. When I add this bulb in parallel, then the resistance of this circuit is going to go up or down? Down. Parallel circuits is adding lanes to a freeway. So the resistance goes down, so the amperage will go up. So now for 2-bulb in parallel, I'm at about 1/2 an amp now. I'm at 496. So this is series. All right. Then for parallel, So 2 bulb parallel, 0.496. If I go and add a 3rd bulb in parallel, which isn't even in the lab, but if I were to do that, then the amperage will increase because the resistance is decreasing. So now we're at 0.734 of an amp. All right. So that's it for this lab. I'll have some questions for you on Canvas to make sure that you do the quiz for this. But that's the end of it for this lab, Lab 14 out of your lab book.